Last week, we've built a computer that can run a code, machine language code. 2 weeks ago, we've actually programmed in machine language, but we didn't really program in binary code, but rather in assembly language and some kind of nice syntax. So there is a gap in the middle, and the gap is supposed to be a simple software program called an assembler. So specifically, you've seen this slide already twice. 2 weeks ago, you've seen this slide to focus on the left-hand side on the actual assembly language format in which you were supposed to program. That was your perspective 2 weeks ago. Your perspective last week was what happens on the right-hand side, the machine language, since you had to actually construct a computer that can actually execute the ones and zeros that you see on the right. Our focus, our perspective this week is going to be in the middle. How do you go from left to right? How do you do from left to right? How do you do the operation, the assembly operation, i.e., what is the assembler, which is the program that translates what you have on the left, the assembly language code, to what you have on the right, the machine language code. Now notice that for the first time in this course, this is software. This is going to be a program that takes as input a file written in the left-hand side format, i.e. in assembly language, and produces another file that's written in the right-hand side format, i.e. Zeros and ones, which directly can be executed in a computer. So this is a software. The first time that you do software in this course, until now, it was always hardware. And it's really the first software layer the first software layer that basically we have in every computer. There's much more software above it, but this is the first level, and we're doing it together with the hardware to give us a complete picture. So we can have a computer that we can understand how you program it, and understanding how you program it does not mean programming it in 0 and 1s, but rather in assembly language, which is still a very, very low format, essentially equivalent to machine language, but still it's something that humans can relate to. So let's see what kind of software is this going to be, this assembler. In principle, we've only created a computer that can run machine language code. So in principle, we should write our program in the only language that can be directly executed, i.e. in machine language code in 0s and 1s, which is going to be pretty annoying. But the best way to think about it is that we're not constructing the first computer in the world, but rather the second one. So let us assume we already have a computer that can run some high-level language. In particular, I'm talking about your computer and the high-level language that you already know. So we're going to write the assembler in that language, and it will be a software program that runs on your computer. What it's going to produce, the machine language it is going to produce, is machine language for the hack computer, for a different computer, the computer on which you will actually run the produced program. So we're thinking about a cross-compiler, sometimes it's called. It's running on one computer and producing code intended for another computer. This way, we don't have this loop, we don't have this bootstrap problem of having to write our assembler in machine code, but rather we can write it already in the high-level language that we've already implemented on another computer. So the assembler program is really a very simple program. It does the following basic loop and repeats it again and again. It reads one assembly language command from the input. It basically breaks it into its parts, and each one of its parts can be translated to binary in a unique way that's specified by our language. And then we take the binary code of the different parts, put them together, and we get the machine code that directly is equivalent to the assembly language command that we've just read. We output that, and we move on to the next assembly language command. We keep on doing that and translate one command after another without having to remember anything that happened in the history. Very simple. So let's look at the different stages, each one of these different stages, slightly more carefully. So how do we read the next assembly language command? Well, it seems that we just read the next line from the input. This is almost exactly what we do. The only other difficulty is that we may need to skip what's called white space, for example, comments. We need to make sure that we read what is really the next command and not any kind of comments or any type of spaces or blank lines that are read there. So when we read it from the file, we have a file that, let's say, has a command load R118, and this is just a fictional language, assembly language. Later, in the next unit, we'll start actually talking about the hack language specifically, but in this unit, I'm still focusing on a generic assembler program. So let's assume that our hypothetical assembly language has this type of command, load R118, which we expect would probably mean taking the value 18 and putting it into the first register. But this is not something that we need to know when we're actually doing this translation. We actually want to read that command and put it into some kind of string variable, into some kind of array of characters that we can later work on. And that is basically what's involved in reading a line by line from the input. So the next step is taking this string of characters and breaking it into its different parts. So when we look at it, we see that the different parts of this command are load, first part, R1 should be the second part, 18 should be the third part. Each one of them has meaning. And there's also a space and a comma, but these are not really the interesting parts of the command, but rather just some syntax which helps us break and understand what's written, the important part in the command. So the next thing we have to do is basically understand the syntax and break the original string into these three different, if you wish, substrings, the three different interesting parts that are involved in this command. So that involves basically some kind of simple string manipulation until we get the different parts. Once we have these different parts, then we need to translate each one of them to machine language, to actually its binary counterpart. Now, how do we do that? That has to be part of the specification of the machine language and assembly language. Basically, it tells us what is the code for each one of these commands, for example. So for example, the load command, we would probably have some kind of table which tells us what is the machine language code for each command. In particular, we can look up in that table and see what is the machine language code for the load command. Other parts of the input may be, for example, numbers, or maybe other things that we can directly translate into machine language just because they are number. For example, the number 18 may be translated into the binary representation of the number 18. Again, this is part of the language specification. This is the basic part. This is the part where we need to understand exactly the mapping between assembly language and machine language, which is usually very simple and specified completely by a bunch of tables and a bunch of rules of where do you put integer numbers in the binary form, and that's about it. The third part is now we have basically the translation of each part of the input, and we need to put them together. Usually it's just some kind of concatenation. Maybe we will need to put also some kind of other bits that are defined in the specification to actually pad them and complete the language, because that's how to translate it. This is the easy part. But what happens the first time we see this variable weight? Well, we look at it, we look in the table, and we see that it's not there. So we know that we need to allocate a new memory location to hold this variable. And this is one of the things that our assembler will have to do. So it will actually find the next memory location that's available. And the exact definition of where does it allocate memory addresses should be part of the assembly language specification. And it will basically allocate this new memory to this symbol. And now it has this pair of symbol memory address that it can put into the table and use from now on, including for now. And this is how basically we put variable locations into the table and how we use them. The other kind of symbols that we have are labels. So let's see, for example, we have a piece of code that has in it a label loop. What does this mean? When our assembler actually looks and reads this line, label, it knows, well, this is just a label. It's not a real command to execute, but I have to remember that the next time somebody wants to jump to this symbol loop, I have to remember where exactly it is. Where is it? Well, I have to remember what address is the current command going to be put into the memory, and that is going to be the address that's referred to by loop. So, for example, if this current piece of program is being allocated into being written into memory locations 671, 672, 673, and so on of the program memory, when we see this label, our assembler will have to remember, the next program is program 673, so I need to remember that loop from now on always refers to location 673. And this is basically the kind of thing that it needs to do. And then when we actually get to a place that uses this label, uses this symbol, then we already know, we already have in our table what exactly is the correct address. So that's basically how information is about labels is put into the table and read from it when needed. Now there's one extra complication that we didn't talk about, that sometimes we can jump into a label before the label was actually defined. This is called a forward reference. So for example, it's very common in programs that I will need to jump, let's say, into a label called continuing, cont, before the label actually occurred in the program. If that is the case, when I reach the first jump, the jump instruction that uses a label, that happens before I've already seen the place that defines the label in the label command, and how can I handle that? Because it's not in the table yet. Well, there are two ways to handle it. One way, which is usually a little bit more complicated, is to basically remember that I've seen a label that I don't know where it is yet, keep it in a side table, and when I actually get into the definition of the correct address, fix it back. Another option, which turns out to be sometimes easier, is that I actually do everything in two passes. In the first pass, I read everything only paying attention to the labels and remembering where each label refers to. That's when I actually build the table for the labels. And only in the second pass do I actually go and convert each and every label into its correct code, into its correct address that now is already in the table because I've put it there in the first pass. And that's usually slightly easier to do, but you may use each one of these two possibilities.